Here is a question that I'd like us to think about as we go through this video. In TensorFlow, a program is represented using a computation graph, which is a DAG, that's a directed acyclic graph. The question is, what do the nodes and the edges in this directed acyclic computation graph represent? Again, what do the edges and the nodes in a TensorFlow computation graph represent? The key to working with TensorFlow and the key to making TensorFlow work for you is understanding the computation graph. This is the central abstraction of all operations in TensorFlow. If we understand this, we have a fighting chance of creating pretty complex neural networks with a minimal amount of effort. In TensorFlow, everything is a graph. This is an abstraction that works really well with neural networks because, after all, neurons tend to be interconnected in a form of a network. That's the whole point of a neural network. And this is also why TensorFlow lends itself so naturally to working with neural networks. In a computation graph, the edges are going to be data items and the nodes are going to be computations. As we shall see in just a little bit, an individual neuron can be thought of as just two computations. So, really, each neuron is a pair of operators. Those operators or operations can be pretty simple, but they transform data. And the edges in that computation graph are the data items. Once again, the idea of data items being the edges in a graph where transformations on those data items are the nodes. This is hardly unique to TensorFlow, but it does lend itself really well to machine learning and neural network applications. So TensorFlow has made this paradigm its own, and the data items which flow between the nodes are called tensors. This is a standard word, again, not specific to TensorFlow. Tensors refer to any data of different dimensionality. More on that in a moment. So, tensors are flowing through the computation graph. This flow of tensors is set up for you by the tool, and that's where the name comes from, TensorFlow, which is all about the transformation of tensors via a computation graph. Let's understand how this could work with a simple operation which has nothing to do with machine learning. Let's just say that we have a really simple arithmetic operation. We'd like to calculate a certain function. This is represented using a computation graph with two inputs. Let's call these inputs A and B. Nothing too profound here. And this computation graph that we see represents a specific function. That function is y and given by this expression that you see on screen now. The crucial bit to remember is that individual neurons perform operations very similar to these: rounding and flooring, addition and multiplication. This is not all that different from what an actual neural network would do. It's just that the number of nodes would be far greater than what we see on screen right now. More on neurons later. For now, let's just understand the computation graph. We can see that this is clearly a directed acyclic graph. That's a type of graph in which there are no cycles and in which all of the edges point in a certain direction. Here, the edges point forward, i.e., towards the result. The directed acyclic graph clearly has dependencies, i.e., nodes can depend on other nodes. For instance, here, the rounding node is going to send its output into two other nodes, the addition and the multiplication nodes, respectively. This also illustrates the fact that a node can send its output to multiple nodes. It can also receive inputs from multiple nodes. Dependencies are important in TensorFlow for a couple of reasons. One, they help with parallelization because a graph can be split into components which can then be evaluated in parallel provided each of them has no dependencies on any of the other subgraphs. Understanding dependencies also help with lazy evaluation. This means that TensorFlow can only evaluate that portion of a graph which really needs to be calculated for the result to be returned to a user. Imagine a network where an input comes into a node. This node represents the floor operator. The output of that node, that is the floor of the input that came in, gets passed to an intermediate node. This is an addition. This will carry out the addition of that floored input with something else. And then the output of that in turn goes to yet another node, which is a multiplication operator. And so on and so forth. The process continues until at some point a final output is calculated. As far as that final node here is concerned, all of the nodes which come before it are dependencies. The nodes which lie immediately before it are direct dependencies. but all of the other nodes are indirect dependencies. So in order to calculate the output of that final node, we are going to need to know the outputs of all of the dependencies of that node. It's important to realize that in a directed acyclic graph, control or data will only flow from the input towards the output. This is basically true for any sub portion of the graph. It's not possible for any directed acyclic graph to complete its computations if it has a cycle. So, this is really important. A directed acyclic graph, by definition, does not have any cycles. If a graph did have cycles in some way, and if we created a cycle by somehow artificially reversing the direction of one of the arrows, then our computation would never finish. Because clearly, in order to calculate the value of each of the nodes, we would require its dependencies, and those dependencies would require the original node. The net effect of all of this is that a computation graph with cycles will just never finish, it will never terminate. It is important to make a distinction between the acyclic nature of a directed acyclic graph and the inherent cyclic nature of the process of machine learning. Let's see why we make that statement. Let's see why we describe machine learning as a cyclical process. The way machine learning works, we have a corpus of data, we pass that into some bit of software which performs feature selection and machine learning, and we get an output. So far, so good. All of the directionality here is forward. But now remember that a machine learning algorithm is one which changes its parameters or it changes itself in some way based on the input data. So, given a set of training data, we are going to calculate the loss or we are going to calculate the performance of our machine learning classifier in some way and feed that information back into the machine learning algorithm itself. And straight away, you can see that we now have a cycle in this graph. This is not a computation graph, just to be clear, but we do have information which is flowing backwards. And it's important for us to conceptually understand how this backward flow of information changes the machine learning algorithm. Any machine learning algorithm is going to have some internal state. For instance, in a neural network, we have different layers of neurons which are connected to each other in complex connections. But that could also be a lot simpler. We might just have one linear regression going on where the only state that we have is the equation of a straight line. Whatever that internal state needs to change based on the performance that we had versus the training data. For instance, we might change the slope of a regression line or the weights of neurons in a neural network. And those changes are carried out for us by TensorFlow during the training process, provided that we set up the loss function and the feedback loop correctly. So, how does this feedback mechanism relate to that directed acyclic graph which we discussed a moment ago? Well, it happens via a mechanism known as graph unrolling. Let's see how this plays out. Clearly, as always, we are going to have a directed acyclic graph. This will have data flowing into computation nodes and the results flowing forward. But now, during the training process, the outputs of those results later on in that process are going to be fed back into a new iteration, a new version of the graph, which in a sense will have some different weights, some different parameters. These form the feedback mechanism. That feedback mechanism might, for instance, change the slope of a regression line based on the data in the training set. The way this happens is by unrolling the graph through time so that each training step seems to represent a different graph, and the output of each training step is then fed in as the input of the subsequent training steps graph. Just to be clear, once again, this process is handled for you by TensorFlow, so you don't really interact with it or see how it's playing out. But really, this is how training a machine learning model takes place. The computation graph is unrolled, the output from an earlier iteration is fed in as the input parameters into the next iteration. And because the training process can consist of thousands or even millions of steps, it's up to us how often we wish to unroll this. That is a choice which we exercise based on the number of iterations in our training data. Let's return to the question we posed at the start of this video. In a TensorFlow computation graph, the edges represent data items, that's tensors. The nodes represent operations on those tensors. This is important, and this is actually common to most DAG representations of data transformations. In TensorFlow, the edges are tensors. In a technology like Dataflow on the Google Cloud platform, The edges will represent p collections. That's some kind of distributed collection. The idea is common. When you have a set of operations represented using a directed acyclic graph, data flows between the nodes. The nodes represent operations on those data items. Those data items constitute the edges, which of course in TensorFlow are the tensors.